Good morning and welcome to the second webinar in this four-part presentation on implementing an OSHA-compliant arc flash safety program at your facility. My name is Jim Chastain and I wanted to welcome you, appreciate your attendance and support of EasyPower. And I want to remind you that the focus of this series is to give you and your company options to reduce the cost of compliance while increasing the safety of the workplace. Today's modified agenda, I'm going to take some time and follow up some of the questions that were posed from last session, and then as promised, run through a very brief example of what I consider to be the arc flash paradox. Then we'll deal with the one-line diagrams and a brief overview, use of the tools. We'll be focusing next session more so on the tools for analysis, and then getting into a fair amount of detail on data collection. So one of the best comments from last week was the report from a former employee of Dow Chemical in their southern facility in Texas, and that was that all qualified workers are trained that every disconnect requires a label, and every label device requires arc flash PPE. And the comment was, if a disconnect is missing a label, assume it fell off and stop and go back and review study results before you proceed, which seems like very good advice and evidence that the company is supporting very much supporting the safety of the workers. One question came up, do we really need PPE to operate a low voltage breaker or disconnect with the enclosure closed? This actually is a question that's a holdover from earlier versions of NFPA 70E, and specifically what's involved or what's discussed in the 2018 version of NFPA 70E is that under normal conditions, the answer to this question is no. Normal conditions mean that the equipment is installed per manufacturer's instructions, maintained per manufacturer's instructions, all covers and enclosures are properly closed and secure, and there's no evidence or indication of pending malfunction. However, if we really understand the intent of 70E, the 2018 version, we may approach the following situation a little differently. And that is, we've done an arc flash assessment on our plant, and we realize in our older facility that there are some buses that may have or may be suspect as far as their integrity, may have air holes in the dead front, we may have elevated energy behind the closed panel, and yet we still require an operator to frequently manipulate or close or operate a breaker. And so we may come up with a procedure based upon our knowledge now of our system that may require an operator to stand to the side and not in front of the panel or face the panel, have additional PPE on their hand and arm, maybe some hearing protection, and we need to ensure that the operator understands why the purpose of this or why the need for this is important as far as the safety. Now, another question came up, is the minimum PPE rating 1.2 calories per square centimeter or 4 calories per square centimeter? Well, it's kind of the question is a little bit misguided. The arc flash boundary is at 1.2 calories per square centimeter. So that's where the system requires PPE inside of that distance. There is no zero category, which means that below 1.2 calories, the requirement for additional PPE is not required. But again, this will depend upon company policy, and that it requires additional information or discussion about what that means. If any panel that needs to be worked on is greater than 50 volts, then it requires a label. Again, if the operator needs to do it while it's energized and exposes human activity. Often companies will require a minimum daily rating on qualified workers for instance, 4 calories per square centimeter to prevent incidental exposure. And so on our one-line diagram, we may want to indicate that and highlight any bus that has greater than 4 calorie exposure, which again is a company policy dictate. It's not required by NFPA 70E. But the bottom line is, and this is something I'd like to kind of reiterate, even without a PPE below 1.2 calories per square centimeter, we could be exposed to, if our bare skin were exposed to that level of energy, it could mean we could be burned. So even though there's no requirement by NFPA for additional PPE, I think we need to have a discussion as far as company policy requiring unqualified or, anybody in the area, even though it's indicating less than 1.2 calories per square centimeter. The question always comes up about the low voltage exception. And the question was, what about excluded equipment? Below, it used to be, below 240 volts, below 125 kVA supply, the standard says we could ignore those loads as an arc flash hazard. Originally, it suggested that there was less likely of an arc flash at that area, and so frequently that type of equipment was disregarded in terms of doing data collection and included in the model. With the 2018 version of 1584 now coming out, the verbiage here states sustainable arcs are possible but less likely in a three-phase system operating at 240 volts nominal or less with an available short circuit current less than 2000 amps. Well, I admit that verbiage is spongy at best and leaves up a lot to be desired in terms of a well-defined limit. And so at this point, I think that the person doing the study, the engineering resource, needs to apply their knowledge of the system and the procedures involved in a discussion with management to understand what this means in terms of equipment that needs to be labeled or data needs to be collected. So more to follow. Happy to talk about this with anybody else that has questions about it. Now, last week's poll said, asked, where do you stand with respect to NFPA compliance? And it was pretty evenly split between folks that were just getting started and folks that were done or almost done. And so I had a couple things to say about that. Likewise, in terms of what offered the greatest challenge, it was pretty evenly split between getting started and data collection, and then trying to make your mind up on whether you need to outsource some or all of the study itself. For folks that are just getting started, the decision really needs to be made about whether you're going to do the study in-house or you're going to outsource it or have some combination of both. We work frequently with new tool owners to help them review their files, their initial approach, to make sure their mechanics are sound. And then as the data collection process proceeds, once the model's built, we can, quote, file review based on time and materials, and that also can help people assure themselves of the accuracy of their methodology. And at the same time, we also work with people where we send folks, an engineer on site, to do training and get people kicked off on the right foot. So there's multiple levels we can help folks engage. But I do want to emphasize, to make sure you get your team involved, no matter who does the study, because there's a lot of knowledge that they can assimilate, understanding what's being done, but also understanding how important the study and results are as they pertain to the maintenance that needs to be done on the system. But above all, I want to recommend that when you outsource your study, you require that a data file be delivered with the study. And the point is that data represents your plant, and if you've paid for it, frankly, you should have a copy of it. Now, if there's more to be discussed there, be happy to answer or address that if you want to contact us directly. Okay, so that's the list of questions. Now, as I mentioned before, if arc flash is such a big deal, why does anybody delay compliance? And in my mind, the answer is, especially for folks that have been working in electrical maintenance for all their career, there literally could be a misunderstanding of what arc flash is all about. And so I'd like to share this true example with you. Shortly after I joined the company, I got a call from an electrician in Oklahoma who said, "Jim, I've just purchased your tools. I think I found a bug in your system. I have the responsibility of labeling all the above ground distribution system in the oil field here in Oklahoma, and I'd like to go through it with you." So we got on the phone, and we got on a GoToMeeting session so I could show him my screen, and we drew his one-line diagram, and this is how the conversation went. This is the start page for EasyPower tools, and we're going to draw a new one-line diagram. The tool always launches in Database Edit Focus. This white area is where we draw the one line, and we use the equipment palette over here on the left vertical sidebar to do this. The electrician said, "Jim, the first thing I have coming in is my utility." So I left-click once on the utility icon, place it in the center of the screen, and left-click a second time to place the icon there. He said the second item on my one line is a two-winding transformer. So over off the equipment palette, I click once on the two-winding transformer, touch the pigtails, click a second time. He said his utility voltage comes in at 12.8 kV. Everything's in kV, so I type 12.8 into the required dialog box. He says, "Now put a plain bus on the secondary side." So I pick up the bus from the equipment palette, touch the pigtails, click a second time. He said his distribution voltage was 480 volts. I'm going to type in 0.48 for the kV. Now, as I move the cursor around the screen, you can see it takes on a different shape as far as the icon. Here where I have a quad arrow icon, I can left click and drag and move that element around the screen. If I hover over the end of a bus, I show a dual-ended arrow. I can left click and drag and extend or contract that bus as required. He said extend the bus out about half the width of the screen and drop a cable on each end. The cable is this circle with 3 inscribed circles. I click once, place the crosshairs on the bus, click a second time, and I do that another time for the other cable. Now, if I want to not go back and forth to the equipment palette all the time, he said to put a bus on the end of each cable. So I'm going to select the bus, hold down Control, and then I can place as many elements as I want of that particular type. Now we're ready to enter data. So he says this first cable, I'm going to double click on the cable, open up the cable dialog box. There's 2 reasons people really like EasyPower due to its increase in productivity. That in part is due to the left to right migration of the workflow and the fact that every dialog box for the equipment has the same general format. So he said this first cable is US based, number of conductors per phase is 1, the type of cable is a 1C, the insulation is THWN, and the size was 350 kcmil. So we've selected there. What we've just described is a copper conductor routed through a steel conduit. He said this is 50 foot long. So we're typing in 50. Now these red exclamation points indicate that there's missing data. If I use the calculate button, the tool will calculate the ampacity for this particular cable and the resistive and reactive impedance per 1,000 feet. So I'm going to click OK to save these results. Now I'm going to right click on this first cable again and copy. Right click on the second cable and paste, and all that data is taken to the second cable. I'm going to double click on the cable icon to show that it's still here. So you notice we have a unique identifier and the connection points into the system, and these again will be consistent even across other types of equipment. He said the second cable is not 50 feet long, but it's 1,000 feet long. So we're going to put in 1,000 and now click OK. This brings us up to the transformer icon. Double click on the transformer. Now all this information comes from the nameplate. He said, Jim, I've looked at the transformer nameplate. It's an oil-filled class OA, works with a fixed 65-degree rise. It's a delta Y with the Y grounded, and it's a 1000 kVA. So I type in 1000. Now I'm going to go to the impedance tab. We see more red exclamation points. The impedance on the nameplate says 5.75%. Now, we may not see the X over R ratio or zero sequence ratio on the nameplate, but the tool will calculate those for me. And then when we get to coordination, we'll see the damage curves are plotted by default, these check boxes indicating that. All this is per ANSI standard that's required for an oil-filled transformer. Now, the reason I like this example as much as I do, there's one protective device in the system. And the electrician said, Jim, I've opened the utility switch, cutout switch, and looked at the label on the fuse. In this case, we're going to put a fuse switch right below the utility bus here in line and click another time. He says, the label on this fuse indicates this is an AB chance. Now, this is the first dialog box that we've worried about the manufacturer. Built in with the tool, installed with EasyPower tools, is a device library that includes 40,000 entries. And so it's pretty difficult to find a device we don't have listed in the library. He said, Jim, this label on this fuse says it's an AB chance. The type is a fuse link. The style is a fuse link. The model on the label says it's a Model T, and we both chuckled because we thought a Model T in a different context. And it's a size 10. Now what I want to do when I go to short circuit, I want to see one or both of these numbers change when I click calculate. The fact that this X over R test environment change says, Jim, I found the part number you gave me. The manufacturer has a data sheet. He's tested it to an ANSI standard using symmetrical current and an X over R environment of 15. Now normally a protective device has an interrupt rating, but because this particular fuse does not even have a holder, it's just a piece of wire stretched across the switch, it doesn't have an interrupt rating, so we're not going to look at that right now. So at that point, the electrician says, okay, I'm ready to calculate my short circuit current, so we're ready to go to short circuit focus, the lightning bolt at the top center of the screen. I get a new series of icons across my focus banner. He says the first thing we want to look at is half cycle current for a bolted three-phase fault. I'm up at the left-hand corner here showing a balanced fault as a type of fault we're going to use, and we're going to apply the lightning bolt on the far left where we're going to fault all the buses. And at that point we get some numbers and some pretty colors. He says, Jim, I understand this is looking at the A phase. If we look at the B and C, they're all equal because it's a balanced fault by definition. But this indicates if we have a bolted fault on bus 2, each phase will see 20,915 amps coming from the transformer. If we have a bolted fault on bus 3, we'll see 17,878 amps per phase coming from the upstream. He was disregarding the downhole motors, which would be a load on his system, which was fine with me. And he says if we have a three-phase bolted fault on bus 4, each phase will see 4,351 amps. He says, okay, that makes sense. Now I'm ready to do instant energy calculations. The arc flash icon is this little burning man symbol on the top row over here. And when we click on that icon, we get new numbers and new colors. And this is where the electrician says, Jim, I think you have a bug in your tools. So, well, what do you mean? He says, well, right here, I see the arc flash boundary on bus 2 is 20 inches. The instant energy is 1.4 calories per square centimeter, so I know what PPE I need to put on to work on this bus hot. If I go down to bus 3, the arc flash boundary is still 21 inches. Instant energy is 1.5 calories per square centimeter at a working distance of 18 inches, so I know I can basically use the same PPE to work on this bus hot. If I go over to this last bus 4, my arc flash boundary has doubled, the incident energy is almost tripled, and now you're telling me I need to put on more PPE because of the elevated energy on this bus. I said, yeah, what are you trying to get at? He says, well, I've been an electrician for 25 years, and anybody that knows electricity knows the farther away you get from your energy source, the lower the energy is going to be. So what's wrong with your tools? I said, well, Vern, I've been an electrical engineer for 25 years, and I agree with you. I don't understand why the energy goes up. Well, the reason for the story is, and the moral of the story is the value of the tools. Every time you do an arc flash study, you're going to reach the same spot, which is trying to understand whether or not the calculations are correct. And the tool lets me see that by using this arrange for arc icon in the top center of the focus banner. As I invoke that, the tool shows me the one-line diagram and how the calculations are being made down here on the arc flash hazard spreadsheet. It also allows me to isolate on each particular bus. So as I double click on bus 2, I see it's a 480 volt bus. It's a fuse as a protective device. The electrode gap as we defined it was 25 millimeters. We already knew the available current was 20,915 amps. According to the IEEE equations, the maximum current an arc will draw is 14,018 amps for this condition, this fault. According to the data sheet, that fuse will blow under these conditions in 43 milliseconds. We put all that in the IEEE equations. We get the arc flash boundary of 1.4 calories and a working distance of 18 inches, and the arc flash boundary is 20 inches. Let's go down to bus 3, double click to fault it. It's still 480 volts. It's still the fuse as a protective device. It still has a 25 millimeter air gap. But now it only has 17,878, of which the IEEE model says the maximum current an arc will draw under these conditions is 12,060 volts, 60 amps. According to the data sheet for that fuse, the manufacturer says that fuse will clear the arc in 54 milliseconds. We put all those numbers into the IEEE equations. We get an instant energy of 1.5 calories and an arc flash boundary of 20.9 inches. If we go down to bus 4 and fault that, we still have 480 volts, we still have the same fuse, we still have the same air gap, but now the amount of available short circuit current is 4,351 amps, which we knew, according to IEEE, the maximum current an arc will draw is 2,803 amps. According to the data sheet for that manufacturer, it'll take almost 3/4 of a second to clear that fault with the fuse. So that means that if I wore the same PPE that I used when I worked on the transformer secondary, and I went down to work on this bus 1,000 feet down the road, and I accidentally invoke an arc flash, that this explosion will last 10 times longer than it did when I was working on the transformer. So the PPE that I had up there will not protect me from the radiated heat down here. And both the electrician and I simultaneously said, duh, I get it. Time is everything when it comes to arc flash. I apologize if this was too remedial for some in the audience, but the fact is, it's what I claim to be the arc flash paradox. And it was this example in this conversation that actually was an epiphany for me, and I better understand in any given system, I may see higher incident energy with higher arcing current, or I could see higher incident energy with lower arcing current. It all depends on the time it takes to clear the arc. So it's those of us that think we know everything about Ohm's law may not necessarily understand the true phenomena, which is arc flash. Now, when we start talking about construction of this one-line diagram, you can see just from that example that there's a lot of information in the data file itself, and that's why I emphasize that even if you outsource your study, make sure you get a copy of that data file because it has high value for more than just calculating incident energy. Before you start data collection, I suggest you should draw a simple one-line diagram, not too dissimilar from what I just did with the electrician from Oklahoma, but make sure that you understand, or whoever's going to be doing the data collection understands the parameters that affect the incident energy calculations. And so I suggest you start with a very simplified connection between the utility through typical examples of the loads, transformers, switchgear, and ultimately out to however what a typical panel is or motor is that you're going to serve as a load, and make sure you can get the result that you're expecting to see, because if you need to label whatever you're trying to label down here, if you don't have the correct information in that in series 1 line, then you're not going to get the results, and consequently you're going to have to make multiple trips to the site, which causes the cost of the study and the time spent on it to go up exponentially. So again, playing with the tools a little bit, asking questions about the mechanics is well worth the time spent before you start the data collection. So data collection is actually recording the equipment data that's required for the accurate power system modeling and analysis of the facility. And you'll see as we get into the estimated time, normally, unless you have a lot of protective devices that need coordination, the data collection process and building the one-line model represent about 50% of the man hours or people hours that it requires to complete a study. Now, building the model itself is actually drawing the one-line diagram and entering the data that we've collected. As you saw there, while it's relatively easy, there's going to be, the more extensive my one line, the more that particular task involves, and the accuracy and making sure that I take care as I'm doing it will pay off in the long run. One of the handouts that I've included in the control box for the website is Practical Solution Guide for Arc Flash Calculations, and I encourage you to take advantage of it. So it becomes obvious once you kind of play with this a little bit that it is an important step insofar as the data I collect needs to be as accurate as possible. Now, there's going to be some, especially in an existing facility, it's almost a snap in new construction because we have exact links and exact documentation on the equipment. If we're talking about an older facility that could be 25 years or older, it's going to be very difficult to get some information on some of the equipment. And so at that point, you're left to make some assumptions, you're left to do some estimations. These need to be documented, and it's worth spending some time trying to recover any previously detailed as-built or maintenance records or repair systems. Anything you can collect should be included as you're starting the data collection process. And you need to approach it with a plan of attack, not just kind of willy-nilly go out and start writing down numbers. Now, I mentioned earlier the approximate time for data collection is roughly probably 2 hours per substation, and then anywhere from 5 to 10 minutes per load. And then the data entry, modeling, and verification can be anywhere from a quarter of an hour up to a half an hour based upon what kind of data we're trying to collect. Arc Flash study requires both short circuit data and protective device data. And so the main difference is how much data that involves. And as you get into understanding what implications there are reasons to do both a short circuit study first, protective device coordination second, before you complete the Arc Flash risk assessment, because they're all interacting parameters that you're being collected and doing the analysis on. So whenever possible, you want to make sure you're doing data collection on de-energized equipment. And this may mean that you come back later rather than just force ahead during operations. And so that's what I mean by having a big picture plan of attack, and try to limit as much as possible the risks that you have to take, because frequently people trying to remove covers can, if they're not used to doing that procedure, lose their hold on a piece of heavy cover, and it could actually fall into the electrified equipment, causing an arc flash just as a result. So again, safety first during this process, and at the same time, you should look for signs that of irregular operations, whether it's moisture forming or loose bolts and screws, And for sure, as you're doing the work, make sure you do not leave the equipment inside, tools inside, loose terminals or nuts and bolts that you loosened are not accounted for when you put things back together. So as part of the data collection notes that I provided, this list is included, and we highly recommend taking as many digital images as possible. You'll see as we get into modeling the tools, those images that can be associated with our one-line diagram and make it easier at a later date to understand the equipment and correlate things if they're not well documented down the road. So as I mentioned, have a plan of attack on how to do the assessment data collection by section. And then while you're doing that collection, make sure you're doing as much detail in the data on each piece of equipment. And frankly, anything in the medium voltage or higher voltage distribution system is, I guess, more important than some of the panel information schedules that are down in the last leg of that distribution feeder. So as much as, and frankly, the length of the cables is important, and that's probably one of the most difficult things to ascertain as you're collecting data on an older installation. Now I want to talk a little bit about the changes in the 1584 model because they directly impact the data collection process, in that there are typical values that are recommended by the standard, but there are places where a non-standard or customized panel or piece of switch gear could affect the instant energy being calculated. So what's not changing is that the target is still three-phase AC only as far as modeling. The model is only good for 50 or 60 hertz. There's still no equation for single phase, and the voltage range is 208 volts to up to 15,000 volts. Arcing current and time are still the most important factor in calculating instant energy, and again, the behavior of arcs and the laws of physics haven't changed at all either. The major changes involve the empirical equations, where we used to have 4 equations. Now there's something like 10, and they have to be reiterated as far as calculations multiple times, and then correction parameters, adjustments are made based upon the individual system. The enclosure dimensions must be considered, and this is especially if they're non-standard or non-typical for the voltage or the equipment involved. We'll touch on that briefly. There does not seem to be any difference between a grounded and ungrounded system as we used to verify. And reduced current calculations are done for all voltages. And then we'll talk more about this when we get into the analysis presentation. And we talked also about the low voltage exception has been eliminated. So probably the biggest impact on data collection is having an appreciation for electrode orientation. And so we've come up with 5 different descriptions, and 2 are in open air. So there's a horizontal orientation in open air, vertical in open air, and these are described as HOA and VOA. Then in an enclosed box situation, there's horizontal orientation, vertical orientation, and then vertical terminated in a barrier in a closed box. So here's some examples of each. And we saw this example last week when we were talking about the test vehicle, but essentially vertical in an open box, we have the operator standing in the opening, and the bloom pattern or radiation pattern is down and towards the lower part of the body. So this impacts the amount of radiation that comes out towards the thorax and head, which are the focus as far as instant energy calculation and PPE. Horizontal and open air, essentially, and this is a terminals on a transformer, the radiation pattern is directly out from the stub end of the buswork or the termination, and consequently this puts the operator at more increased risk for heat radiation. When we look at vertical orientation, again, the operator standing out in front of this and the radiation pattern is blooming down. This is not dependent upon gravity. This is dependent upon the relative placement of the operator. So if the technician is directly under termination that looks like this, it would more correctly be defined as horizontal because of the radiation pattern and exposure to the operator. That horizontal in a box, kind of a typical bus connection where we've disconnected a breaker that's can be secured in, and without that breaker in there, we have terminations stubbing directly out at the operator. Vertical in a box with no barrier, again, the operator standing out in the front of this, the bloom pattern is down, and so there's a little bit reduced instant energy at the head and thorax. And so this is an example of how that orientation would work in the field. Probably the most interesting is the vertical terminated into a barrier, and this is what was discovered during the testing, is that when there's an insulation barrier down at the base of the buswork, the bloom pattern is straight out. And again, there's more radiation directly towards the operator, and it kind of depends on whether or not the height of the panel is such that this is directed at the head or face. At any rate, in any given installation, we may have multiple electrode orientation or configurations. For instance, we could have vertical in a barrier, terminated in a barrier at the top of a breaker, and vertical in the bottom of a breaker. So the tools allow us to stipulate that both of those can be the case. In fact, we could have all three, vertical, horizontal, and vertical into a barrier. So the guidance is limited in the 1584 model. Some examples are discussed, and I just covered some of those pictures. So it's up to the person responsible for the study to detail the assumptions that have been made. And what I recommend is, we talked earlier, taking pictures that if you have a calibrated eyeball and you've determined that the bucket or the enclosure that you're looking at or the electrode configuration is non-standard, it may be beneficial to have a wooden yardstick or some other element you can put in the frame as you take the reference measurement as you take the digital image. So again, the intent is try to minimize multiple trips to the site and collect data as much as possible and record it specifically in digital images. What we're going to find when we get into analysis is that the adjustment factor for enclosure width and height actually makes a difference in the calculations, as well as the depth of the enclosure. And while the tools record or include a standard dimension as recommended by IEEE model, it's up to us to determine as we're doing the collection how much we differ from the standard dimensions. Now, in terms of other changes in the standard, the 2-second maximum, what some people refer to as the 2-second rule, has been included and is pretty much verbatim. The fact is it was in an annex once before, and now it's part of the main body. So it recognizes the need or the potential, if we have high incident energy due to long trip times on protective devices, and it's reasonable that an operator or technician could remove themselves from the area if a fault occurred, that 2 seconds might be the maximum calculation time or the limit on doing the calculations for incident energy if our operator could remove themselves within that 2 seconds. Okay, so what I recommend is we start with a minimum one-line diagram and make sure I understand the mechanics and the elements, parameters that are needed to do the arc flash calculations before we actually start doing data collection and before we start drawing a very large one-line diagram. For simplicity's sake, the better and the more work I do with a very simplified example, it makes debugging a large system much easier because I know that I have the mechanics down to start with. You'll see as we get into using the tools next week that there's a lot of the ability to use spreadsheet data entry for panels and motor control centers, and the tools make it relatively easy to copy and paste and replicate typical values or feeders or construction just because we've adopted the look and feel of a Microsoft Office application. I do want to mention that we do have a tablet-based mobile app that works on a Windows 10 tablet, and it allows us to incorporate pictures, notes, and sketches, and then transfer that information into EasyPower for our automatic one-line construction, and that's available as an app downloaded for free from a Windows App Store. It's called OnSite, EasyPower OnSite, and you're welcome to contact sales@easypower.com to hear more information about that. Thank you for attending today. 2 weeks from now, we will be doing the third installment, which is actually EasyPower Arc Flash operations using Arc Flash Suite 2, and we will be going through the steps involved in an Arc Flash study, including protective device coordination. I do recommend, if you have additional information, that there is available on the web these documents that are highly valuable if you want to get into the details of Arc Flash calculations. And so I leave that with you. The Practical Solution Guide to Arc Flash is on Amazon. I think Jim Phillips' guide to hazard calculations is also on Amazon. And then Industrial Power System Grounding Design is available if you contact the website. And these are all on the EasyPower Arc Flash reference page. Due to limited time today, all questions will be answered via email. Thank you again for attending, and very much thank you for the support of EasyPower. Have a good day.